Hello everyone, and thanks to be here. I'm Gregorio. I will talk to you about native, and we will go into details shortly after I tell you just something about me. I work as a DevOps and cloud engineer in ThemeWave. It's the first logo. I am a community manager for GDG Pescara, Google Developers Group in Pescara in Italy. I am a Cloud Innovator Champion for Google and a MIA platform expert. Okay, we will talk about native, but from a perspective of cloud native. Why is that? We will understand it shortly. What I want to ask you is how many of you deploys their application on a cloud provider? Okay, some of you. And what's the first stress that you leave, like performance or I don't know, bills and so on? That's why we need to talk about native, but starting with cloud native. And let's understand what cloud native is and why we need to adopt a native compilation to start achieving the cloud native idea. I will present you the cloud native technology with the words that Priyanka Sharma uses when she talks with non-tech people, when she goes out on herself with friends. She says that technology is when engineers and software people utilize cloud computing to build tech that's faster and more resilient. And to do that, they need to do that to meet customer demand really quickly. So that's something that should tell us to start thinking about the technology and the innovation in technology. The three major cloud providers, any one of them gives a detailed description of what cloud native is, and all of them talks about three pillars that are microservices, containers, and orchestration. So basically, we talk about cloud native when we start using this kind of technology. Well, starting from this kind of technology, so microservices, containers, orchestration, what we face? First of all, scalability. We put our services in a container so we can take it, give it to an orchestrator, and start scale out when we need it. Well, we need to allow the cost optimization and the to start perform better. We also need to lower the cost, and that's a big problem, because if we start growing in resource request, the cost doesn't low. So we need to start thinking about how we design our application and how we use resources the better way. And we also talk about higher availability, and that's why we put auto-scaling and self-healing and so on. Well, we can say that the cloud-native application make the most of modern infrastructure's dynamic, distributed nature to achieve greater speed. We said we need speed, agility, scalability, reliability, and cost efficiency. This is a synthesis of the three links that was on a previous slide. And what we are interested in are these three words that are in bold: greater speed, scalability, and cost efficiency. Okay, When we talk about, let's go back just a moment, greater speed, scalability, and cost efficiency. Well, we need to have a smaller memory footprint. We can't have a lower cost if we don't have a smaller memory footprint, but we can't scale out the best way with a big memory footprint. Also, we need less CPU consumption, so basically resource consumption. And also we need a lower startup time. My work on the GraalVM native compilation started when in my company we had a problem with some microservices that started up in 17 seconds. They had a lot to do at startup time. We needed to ensure that they could answer, so produce a response in 5 seconds. So imagine, I can start a new instance of that service that will go up in 17 seconds, but I need to produce a response in 5 seconds. So I need replicas. And when I need replicas, I'm using, with 17 seconds of startup time, I'm not using the resources the best way. So it becomes a cost. Okay, let's go into the detail of the frameworks. We talked about microservices. That's one of the pillars of the cloud native technology. So what about what can we do with the technology as for today on the JVM microservices frameworks? And we are talking about Quarks, we are talking about Spring, we are talking about Micronaut, but we are also talking about everything that runs on JVM, because these are three of the more tested frameworks that works on GraalVM and GraalVM native image. But we can also use, for example, any one of you knows the logo? That's the logo of Ballerina. That is a language designed to run on JVM and to be cloud native by design. Well, that's a nice framework, a nice language, and it runs on JVM. We will talk about Spring, and the demo starts with the classic pet clinic. What I want to show you as for now is just how much time it takes to start up pet clinic on my machine. It's a limited machine, it's a MacBook Air, so I have just a few RAM and resources are not a lot. Let me zoom, okay. As you can see, it takes some seconds, and it should be okay. 12 seconds, 13. It's a lot of time for pet clinic. And if we think that we should be efficient on resource utilization and so on, that's not a good thing. Okay, the talk is named The Good, the Bad, the Native, as for a movie from Sergio Leone. I don't know if you watched it. The movie is called The Good, the Bad, the Ugly, and I will start referring to these three, but not from the good, but from the bad, because 12 seconds on my machine, even on my machine for pet clinic, is bad. So, what would the bad say seeing these startup times? He will say, those bastards out there want more memory, and I have just a few resources. How do you think I can scale or lower the cost? It's impossible. Even with a lot of optimization on the application side. So we have to do something more on the infrastructure side. One solution is GraalVM. So let's start from the scratch and let's understand what a VM is, what the JVM is. It is an abstraction of an underlying machine, the actual machine, and it interprets the bytecode. Well, it's not about only interpreting it, because when we compile and we have a bytecode, we can give it to the hotspot, so the Java virtual machine. The hotspots can do two things: interpret it and compile it just in time. What we will have in both cases is a binary code that can be executed on the host machine. Also, the hotspot will perform all of these operations, so garbage collector, thread management, memory management, and so on. Well, let's see what happens here. We said that bytecode can be interpreted and compiled. How it is done and when it is done. The first step is the bytecode gets interpreted by the interpreter that is really slow compared to the other option that we have. It interprets the bytecode, so the bytecode doesn't get compiled in binary code, and it has a fast startup. It starts collecting profiling informations. That's the key of the way that the hotspot virtual machine works. Because when collecting those profiling informations, we can, the hotspot virtual machine can find out if a bytecode gets hot. When it starts getting hot, it will be compiled just in time by the C1 compiler. It's the first level of compiler that we get on the hotspot virtual machine. So, more frequently the codes get used and executed, more likely the C1 will start compiling it, and we have something that is compiled and executed after the compilation and not interpreted. That's faster than the interpreted version. It still continues collecting profile information. Why is that? That's because we have another level of compilation, C2. When the code keeps getting executed, so the first level of compilation tells us, look, this code is getting executed and executed. Maybe it is convenient that we optimize it and then recompile it after optimized. Well, the C2 compiler takes that bytecode, optimizes it, and it compiles it again using the profiling information from C1 and the interpreter. That's when high peak performance of the JVM takes place. So usually we will see the C1 compilation when we start working on our machine. The C2 compilation, it's when we warm up, we prepare our benchmarks, and we need all those scripts to warm up the virtual machine. Well, that's because we have to have the virtual machine collecting this information, and the C2 compiler can optimize our bytecode. Okay, what's the difference and what introduces GraalVM? Graal is a polyglot VM, so it means that it can provide runtimes for many languages, also for Python, for Ruby, JavaScript, and so on. I was able to compiling native in a native executable, even an application that uses the polyglot functionality. We have a Graal compiler. So we, the guys of GraalVM took the C2 implementation and optimized it, providing a new compiler, the Graal compiler, with the various optimization. They talk about more than 80 optimization. They are all documented. It removes unnecessary object allocation on the heap, and this means that it can create binary code that performs better. Also, we have the native image. That's something we can achieve with the ahead-of-time compilation, and it will result into a native executable. Okay, what are these components and how they change things? This is the hotspot VM. So we have the VM, the infrastructure where everything runs, the compiler interface. So C1 and C2 have to talk with the hotspot VM via the compiler interface. On GraalVM, we have two different components. We still have the C1 compiler that talks with the hotspot VM via the compiler interface, the standard compiler interface. But we now have the Graal compiler, and this component that is the JVM CI, JVM compiler interface, that has been rewritten totally in Java. These two components are totally written in Java. C1 compiler interface and hotspot VM are written in C. Why this is good? This is good because the Graal and the Graal compiler and the JVM CI component written in Java can get hot. And if they can get hot, the Graal compiler, for example, can get this component, the JVM CI, optimize its bytecode and recompile it to achieve peak performance. So that's a great introduction because everything keeps optimized under the hood. Okay, we also said that we have the ahead of time compilation. What's that? We have an input with our application, our libraries, the JDK. We have the build phase where everything gets analyzed, and we analyze this all this stuff with a static analysis. That's something that gets done without running our application. So the compiler starts to analyze our code, to run the initialization simulated runs, to take snapshots on the heap, so everything that will be put into the heap while running our application gets snapshotted. And again, this gets done again and again. Why is that? Because we have to know point 2, the point we will reach while running our application. When we stop reaching new points, so imagine our application that uses a library. We run the application, but we need to run the library, so we have to reach a new point, our library. But the library uses another library, so we need to reach another point, and that's another loop. When we stop reaching new points, that's when the ahead of time compilation stops. That's not all, because we said that when we run on the JVM, we have the hotspot VM. Well, here we are talking about running native. We are talking about a native executable that will not have a VM. The guys of GraalVM created a new VM, substrate VM, that's compiled with the application, the libraries, and the JDK. It is optimized to get compiled with the ahead of time compilation. It's written in Java. It will perform really good after the ahead of time compilation. All of these will go to the output. We will have our native executable with the code in text section and the image heap in data section. That's needed. This part is needed to achieve an instant startup. Okay, so I guess you already seen this kind of I don't know if I still have no, I don't have it. I already I'll zoom it. Maybe it doesn't. I guess you already seen this kind of execution. It's the same pet clinic, but I already compiled it in native executable. As you can see, it starts in 0.7 seconds. That's a lot on my machine. As you can remember, it took 12 seconds on the JVM on my machine. It is 0.7 seconds now. Well, before we get into details here, we will go back to these slides for a moment and let's get back to what we wanted to achieve. We said smaller memory footprint, less CPU consumption, lower startup time. Well, we now understand that smaller memory footprint, less CPU consumption, and lower startup time can allow us to achieve scalability, lower the costs, and have higher availability. That was the goals of the cloud native technology. Let's get back to our movie, and we have the good that will start sleep peacefully because he knows that the native is watching over him. But we have some drawbacks, and that's where the talks gets interesting. First of all, the native image compilation takes a lot. It took, on this machine, it took like 23 minutes to build. It's a lot. It is difficult to debug the native executable. I've seen a talk by, I don't remember the name of the speaker, but it was a guy from Belsoft, and they have a way to debug the native executable on a Linux machine. It's not friendly at all. And that's because we don't have the source information inside our native compilation, native executable. Well, if we can't debug the native executable in a friendly way, we have to test it a lot. But we have to test it becomes how to test it when it gets compiled in native executable? Well, we have any idea? We have a test content.
I think that you can test before you build the image.
You can test before you build the image.
You can debug the microservices before you.
Yeah, you can.
Build
You can.
the image.
You can test before, but what's in the game is this consideration. The native image generates the metadata, so everything that tell us the point to analysis generates metadata. The metadata tells us what needs to be put into the native executable. Everything else gets stripped. This is a closed world analysis. So everything that gets executed, maybe because we will not execute the application. We will just analyze it in a static world. So the dynamic features such as reflection, dynamic proxying, and so on will not get executed. That's something we will try to understand looking in a static way our code and our libraries. Because of this, the native executable could be stripped of something that we need during runtime. Well, when we test, it's okay to test before the native executable, but when we build the native executable, we could get stripped. The native executable could be stripped of something that it needs, and that's bad. The only way to ensure that we still have everything we need is to test the native executable, and we can test it using the test containers. A real world scenario, so we have our native executable, we put it together with test containers, and we have to perform integration tests, not just unit tests, but also integration tests. Okay, it is not easy to create all these metadata. We are going to see them, but when we are stuck and don't know what metadata is missing, the tracing agent can help us a lot. The tracing agent is a jar that we can instrument, and we can execute our application with the tracing agent. It will generate every metadata that the application needs, and we can tell the ahead of time compilation to use that metadatas. We can see what the ahead of time compilation did here. Okay, we have GraalVM reachability metadata. These are the metadata for everything that is used by my application, so every library. And also we have the Spring IoT metadata. For example, we have resources, metainf, native image. This is where we can add the metadata when we need to instrument the native compilation about what our application needs. This is an example on the proxy configuration, but we also can see the reflect. So this is the configuration for the reflection functionality. And you can see, for example, let's get something more. Okay, for example, for Jackson parameter names module, we have to expose all public methods because they get queried, and all declared methods because they get queried. That's something that is provided as for now by all the libraries that are used in Pet Clinic. Various open source projects are adding reachability metadata on their code, but not everyone is ready as for now. And that's something that gets complicated, because when you can't understand which component is missing those metadata, the only way to solve the issue is running the tracing agent. I don't know if you've seen the presentation by Alina yesterday. She, for a moment, ran 3 different benchmarks, and the third one was the one with the peak performance. Well, the second one was the benchmark on the native executable, and one would say, well, I created that native executable, I would expect the performance to be good, even better than the JVM version. Well, that's not real, because we have peak performance on the JVM when the C2 compiler gets into the game. And the benchmarks on the JVM are instructed to activate the C2 compiler. So that first benchmarks used some instruction that activated the C2 compilation, and that was the real peak performance of the JVM. What does this tell us? JVM is a really good product. It has a really good performance, and it's not really easy to have performances on the same level. If we want to have the same performance, we have to instruct even the native compilation. Some libraries, as I already said, does not provide good enough reachability metadatas. Some include dependencies that we may need to manually exclude. I will tell you about an example. I can't provide it because Google already patched the libraries. So when I started to create the example, it was already solved, and I was not able to find the right version with the problem. The Google API client library had an issue because it included the common logging library. That's not an issue when we run on the JVM. It runs smoothly, but Spring uses another logging library, and when we use SL4J wrapper, it will instantiate one of the implementation that are inside our jar. Well, the native compilation will not use 2 different implementations. It will use one of them. But we had 2 different implementations, the one from Spring, the one from Google API client, and that was in conflict. So when the application started, it was using the Spring provided implementation, and it was good. When I executed the controller that used the Google API client, it tried to use the common logging implementation, and it was a nightmare because it would not find it. what's the solution? We have to manually exclude this kind of dependencies. That's not something that we can find out before. We have to find out by running tests, and we have to understand it and manually exclude the dependency that is creating the issue. Also, it is better to avoid shaded libraries. If you don't know what a shaded library is, when we shade something, it is just that we are using some dependencies and we are providing a closed use of those dependencies. So we don't want another one of our dependencies to get modified, for example, on the version. So we change the names of our dependencies. That's what the shading does. Netty provides a shaded library, and it provides shaded libraries on gRPC too, and that's why that's because gRPC with netty shaded doesn't work with the native compilation. We have to use the unshaded version. Let's get to the third character of the movie. The native in the movie is called the ugly, Tuco. If we want to go native, there is no shortcuts. We have to go native the full way. So we have to start working on everything that it means. Libraries that have dependencies that should be excluded manually, and tracing agent, and so on. Let's get back to the words of Priyanka Sharma. We said that when we talk about cloud native technology, we are talking about innovation, basically. Well, we have seen that we can use the GraalVM native image, and we should start using it. It is getting more and more production ready. It is getting more and more interesting. If not the native image, we should start using the GraalVM without the native image, because it is a great implementation with great optimization. When we go native, we should use the tracing agent for sure, because it solves a great issue that will take us times to solve on our own. Also, we should use test containers to test our native compiled application. So that's a great idea, using containers to have real scenarios with the real applications. These are some links for the documentation on GraalVM and the native image compilation starting from Spring. I also added the one from Quarkus because it provides a lot of insights on how the native compilation works, and it is written very well when everywhere, but the starting piece, when they say how it is done, is written very well, and it helps a lot to understand how it works. I'm done with this slide, so if we have some questions, feel free to ask. Just after.
I've used the native compiler for projects recently, and
Sorry?
I've been using the GraalVM native image recently, and the metadata is the thing that keep struggling with. Am I right in thinking that the tracing agent only works with the Graal JVM?
Okay.
Or is that?
Okay. It works only with the GraalVM because it is created to work on the GraalVM. So it will use the same mechanism that the GraalVM expects to be used when it performs the ahead of time compilation. So when I can get back to the slide. Okay. This kind of analysis is in GraalVM only. That's why the tracing agent works on the GraalVM only, because it will need to generate information that are needed by this phase, but this phase is present only on the GraalVM. That's why we need to execute on the GraalVM.
And as a follow-up, when you've got the metadata that the agent has produced, it looked to me as if that includes metadata from everything, and so duplicates the things that you've already brought in from libraries and runtime hints.
That's something I've noticed too. And I usually try to, well, this is not, this is true since like 3 or 4 months. Back, 1 year back from now, it was not true because there was a lot more libraries that didn't provide metadata. But as for now, there are a lot of libraries that already provide them. When I started back 1 year back ago, I used to try to provide the metadata on my own. And when I didn't succeed, I ran the tracing agent, and it will tell me basically everything. I will start picking the single metadata that was notified me by the run that was failing, and adding it. It is something that requires time because you know, you run, the run fails, you add a metadata, and you hope it is the only one that is needed. So it is not really practical, but that's the only way that I know that works when we don't want to include basically everything that the tracing agent tells us.
Yeah, okay, so that mirrors my experience, that you're either guessing from the error and adding it, or maybe picking a class out of the whole generated list.
That's a pain, actually. That's a pain.
Yeah, thank you.
We have.
Do we have an opportunity to integrate ArcUnit to test the native image, or we don't have that way open?
I don't know. And it would be nice to go into details. I don't know.
That's a good one, because not the code before the compilation, but we can test the image after the compilation with some rules.
It should work, but I didn't try it. But that would be a nice thing to try out.
That's it.
Okay, my question is that you said that we don't want to include everything that the tracing agent gives us to the to this hint metadata. Why don't we want to do it?
Okay. The tracing agent collects metadata on everything, and that's something that based on my experience, but it's backed from other one's experience. So when we include everything, our native executable is not stripped by things that it doesn't need. It's not bad to have everything. It's just that we can have just a slight better optimization.
Okay, thanks.
Other questions?
There is two consequences on the build, on the resource needed for the build. The more reflections or proxy you are declaring, the more resources you need to compile natively the image. And sometimes when you're including a lot of reflections, you have a lot of memory during the build, and you have to have very big CI machine to do the build.
Okay, I guess, yeah, we don't have any more questions. Okay, thank you everyone.